Hello everyone, welcome back. In this video, we are going to solve LeetCode 242 valid anagram. This is an easy level problem, but it is very useful problem for understanding frequency counting, which appears again and again in string and array questions. So let's first understand the problem clearly, then build the intuition, write the code, dry run it, and finally discuss the Unicode follow-up. We are given two strings s and t. We need to return true if t is an anagram of s, otherwise return false. Now, what exactly is an anagram? Two strings are anagrams if they contain exactly the same characters with exactly the same frequencies. The order can be different. For example, s equal to anagram and t equal to this anagram. The output is true. Why? Because both strings contain exactly the same letters. If we count them, A is 3 times, N is 1, G is 1, R is 1, M is 1 times. The order is different, but the character counts are identical. Now look at the second example. S equal to rat and T equal to car. The output is false because the first string contains RAT where the second contains CAR. The frequencies do not match. Before doing anything else, there is one very simple condition we should check. If the lengths of the two strings are different, can they ever be anagrams? No. For example, S equal to ABC, T equal to ABCD. The second string has an extra character. So if length of S is not equal to length of T, we can immediately return false. This gives us our first optimization. One very straightforward way to solve this problem is to sort both strings. For example, S equal to anagram and T equal to the nagaram. After sorting both, it will become AAAGMNR. If the sorted strings are equal, then they are anagrams. So we could write something like this. Return sorted of S equal to sorted T. This works, but sorting takes n log n time. So can we do better? Yes. We can solve this in linear time using frequency counting. The problem tells us something very important. Both strings contain only lowercase English letters. That means every character belongs to A to Z, small a to Z. There are only 26 possible characters. So instead of using a dictionary, we can create a fixed size of array of length 26. Initially, we will create a frequency array of 26 length. Each index represents one lowercase English letter. Like imagine this is our frequency array and the length is 26. The first index, that is 0th index, will be for A, and the index 1 will be for B, and for index 2 will be for small c, and the 25th index will be for Z. Now we need a way to convert a character into its corresponding index. We can use ordinal value. Ordinal value gives us the ASCII value of the character. So ordinal value of character minus ordinal value of A will give us the required values. So let's suppose the character is small a. So the Unicode value or the ASCII value of small a is 97, right? So if we do like ordinal value of character, that is a, will return 97, and 97 minus 97, it will become 0. So a will be uh, a will be assigned here, right, for 0th position. Now if we think of B, then B ASCII value is 98, then 98 minus 97, it will become 1, so it will be assigned here. So in this fashion we will do. Now the solution becomes very simple. For every character in S, increase its frequency. Then for every character in T, decrease its frequency. If both strings contain exactly the same characters the same number of times, then all frequencies should eventually return to zero. Let's understand this with an example. Suppose S equal to anagram. After uh, processing S, our useful frequency become A equal to 3, N equal to 1, G equals 1 because G appears only one time, A appears 3 times, and R presents one time, and M is one time. Now we will process T. Every time we see a character in T, we will subtract 1. So uh, when we see N, so N is one time, so we will decrease the count 1 to 0. And if we see A, then we will decrease the count 3 to 2. Now G, we encountered G, so we will decrease the count to 0, and again it is A, so we will decrease the count to 1, and R is one time, A is one time, and M is one time, all will become 0. Everything becomes 0. Therefore the strings are anagram. So can we detect failure early? Yes, while processing T. If any frequency becomes negative, we already know the strings cannot be anagrams. Why? Suppose S equal to rat and T equal to car. So after processing S, the R occurrence is 1, A frequency is 1, T frequency is 1. Now process T. The first character is C, right? But C never appeared in S string. So its frequency becomes C equal to -1, right? So the moment a frequency becomes negative, it means T contains that character more times than S. So we can immediately return false. Now let's write the complete logic in simple steps. So if the lengths of the two strings are different, we will return false, and we will create a frequency array of size 26. For every character in S, we will increase its frequency. For every character in T, decrease its frequency. And if frequency becomes negative, we will immediately return false, and after traversing, we will return true. Now let's convert it into Python. First, we will check the length. If the lengths do not match, they cannot be anagrams. Next, we will create a frequency array of length 26 for all the lowercase English letters. Now we go through every character in S, we convert the character to an index and increase its frequency. Then we will process the second string, we will calculate index, ordinal value of ch, our character, and ordinal value of a, and subtract 1. Now we check. If the frequency becomes negative, the second string contains an extra occurrence of that character. Finally, we will return true. If we complete the entire loop without finding any mismatch, the strings are valid anagrams. Let's dry run. These are our string S and T. Both lengths are 7, so we'll continue. If the lengths were different, then we will return false. But the lengths are same. Initially, the frequency or arrays will have all zeros. Now we will traverse S. First character is A, so frequency of A will be 1. Next, the second character is N, so now the frequency array will contain N equal to 1. Now the third character is A, so the A frequency will be updated to 2. After that, the character is G, so G will be 1. Now R frequency is 1 now. Now again A, the frequency will become 2 plus 1 3, and last finally M 1. After traversing the complete first string, we have this frequency array. Note that all the other characters frequency are 0. The first character is N in T string. So we will subtract from N frequency by 1. 1 minus 1 is 0. Now the second character is A. So we will decrease A by 1. So 3 minus 1 is 2. The next character is G. So G will become 0. The next is A. So we will again decrease to A by 1. So 2 minus 1 is 1. After that R will become 0, and A will become 0. Now M will become 0. All the characters frequencies balance down, therefore output is true. Now consider this example. Lengths are equal, so we will continue. Now traverse S string, so the R frequency is 1. Now A frequency will be 1. Now T will be 1. Now traverse the T string. The first character is C, so we will subtract 1 from the frequency of C. But C was 0 in the frequency array. Now C will become minus 1. Our condition, this frequency, if frequency it becomes less than 0, then we will return false. And that's the correct answer. You might wonder, why aren't we checking all 26 frequency value at the end? We could, but because we already verified that both strings have equal lengths, and while processing T string and we return false, whenever a count becomes negative, completing the loop successfully means the frequencies must balance. So an additional final scan is unnecessary. Now let's run this code once. Now time complexity. Let n be the length of the strings. We traverse s string once, so big O of n, and then we traverse t once, so big O of n again. So total time complexity is big O of n. Now space complexity. Our frequency array always has exactly 26 elements. It does not grow with the input size. Therefore, the auxiliary space complexity will be big O of 1. So overall time complexity is big O of n and space is big O of 1. This is better than the sorting solution. We would require approximately big O of n log n time. Now LeetCode asks an interesting follow-up. What if the input strings contain Unicode characters? For example, instead of only lowercase English letters, the strings could contain characters from Hindi, Chinese, Japanese, accented characters, symbols, or many other scripts. In this case, our fixed array of 26 characters will no longer work. Why? Because ordinal value of character minus ordinal value of A assumes that every character lies between A and Z. For arbitrary Unicode characters, we do not know beforehand how many different characters may appear. So we should use a hash map or dictionary. So the code of Unicode friendly solution will be look like this. Here the dictionary stores only the characters that actually appear, so it can work with arbitrary Unicode characters. And the time complexity will be big O of n because we traverse the array only once time, and the space complexity will become big O of k, where k is the number of distinct characters in the input. For lowercase English letters, k can never exceed 26, but for Unicode characters, the number of distinct characters is not fixed. Before we finish, let's quickly look at few common mistakes. First mistake, checking only whether characters exist. Suppose S is equal to AAB, T equal to ABB. Both strings contain A and B, but they are not anagrams. Their frequencies are different. So checking only whether the same characters exist is not enough. We must compare frequencies. The second mistake that forgetting the length check. Checking the length first makes the solution simpler and let us reject impossible cases immediately. Third mistake, using a 26 element array for arbitrary characters. The 26 frequency array approach only works because the constraints say that S and T consist of lowercase English letters. If the character set changes, our data structure may also need to change. Now the important pattern from this problem is whenever a problem asks whether two collections contain the same items with the same number of occurrences, think about frequency counting. This pattern appears in many problems involving anagrams, duplicate detection, character matching, array equality, frequency comparison, grouping strings, sliding window strings problem. So this small problems builds a very important foundation. So let's do a final recap. We were given two strings and needed to determine whether these are anagrams. First, we checked are their lengths equal? If not, return false because the inputs contain only lowercase English letters. We created a fixed frequency array of size 26. For every character in S, we added 1. For every characters in T, we subtracted 1. If any frequency becomes negative, we return false. Otherwise, after processing the complete string, we return true. The final time complexity is big O of n and space is big O of 1. And for the Unicode follow-up, we replace the fixed size frequency array with a dictionary or hash map. That is the complete solution of LeetCode 242 valid anagram.